Anyway, this is basically for lab now because we have a lab, and I know the lab is not due next week. It's actually due next week, but after the exam. But I'd rather go through it now so that you guys are ready for it, and because it takes time for this lab to get set it up really more than actually doing it. Obviously, there is a hiccup there that if first of all, there is the initial overcome that you guys need to do. You need to make sure that you have Java. What is it? Java runtime environment installed on a computer that you need to use, okay? So that's one thing in order to run the simulations. This is not an HTML simulation. This is not a Flash simulation. This requires a Java, and it's a Java applet actually. So let me go quickly to the screen. Let me make sure that I have the right screen. I don't want any wrong screen in here. Make sure I have the lab instructions basically open because I want to go through them. So we have the lab instruction form, which is typical of what we've been doing so far. The change now is that there is this Excel file. So it's a good idea to download this Excel file. Again, if you don't have Excel, it's free for you guys as students. You can download it from Microsoft website and register with your student ID, student email, and it should work fine. Okay. If not, OpenCalc, opens it too, so you shouldn't have difficulty with this Excel file. It is really helpful in a sense that it does calculations for you. Short, if you don't have Excel, you need to do the calculations by yourself, okay? And I'll go through those calculations and explain what they do. The third thing that you need to download is this .jar file. This is the simulator. We will be needing this simulator for some of the other labs down the road. We will be doing an LC circuit. We will be doing an RL circuit, and we will be doing an RLC circuit. And you will notice that a lot of them will use the same file, basically, with the power generator, at times maybe an AC power generator. So we will need them, okay? So you need to download that. Again, that is when the JRE is needed. Okay, Java runtime environment is needed. In the lab instruction itself, you can go and download that part of the software. I already mentioned in a previous message and also in this lab instructions that if you decide you don't need any of this software, and which is justifiably so, especially for this one, and here I'm talking a lot about this one. If you don't do really any kind of applets and things like that a lot, it's a good idea to uninstall it. But try not to do it while the course is in session, because down the road you might need it. So after December 16th, you can go ahead and install this one. If you don't download it correctly, it might be a hindrance in your system. It drains a little bit of the resources of the system. As anything else also with Java or anything else, if you don't have it running, do not default it to run in the background, because this one has tendency to do that a lot, especially there. It's the updater. So try not to have that update running on the computer, because if you see performance problems with your computer, it might be it or other software that is running in the background. So try to, while it's installed, it's running. When you open it, it runs fine, close it, that's it. That's the end of it, okay? And it was in the past. Now I think they improved the security. It was in the past a problem with the security, because it opens a new session basically from your computer, which made it kind of opens the vulnerabilities. Now I think antiviruses had caught up with it, and itself is actually far more secure. And this is true not just for this software or any piece of software you have on your computer. You have to be really mindful of that, because we are, as much as we don't want to leave our wallet or phone or something laying around the street and walk away from it, same thing, you need to take precautions, and you have to be really conscientious, or at least you have that thing in your mind. You have to be an educated person when it comes to online presence. So you have to really have that. And I know that was part of the discussion we had in the first time, when the first topic actually in this entire course, into how to become really aware of these things. And things of this nature. Okay, so that's one thing. Other than this, basically, everything else should work fine. I'm sorry, the syllabus. The rubric is in the bottom in here. Everything is typical from now on. Hopefully, you guys know by it now. Basically, how things are graded. Questions are basically worth 2 points. The objective is worth 3 points, and the table, depending on how many cells it has, it's worth that many points, and everything else. Now, the other things that are different in here, you have to include the Excel file, okay? You have to include that, and that is actually graded. If you don't include it, you're going to lose points, all of them, okay? Make sure you include that. And also, at some point, you'll be graphing. So if you include the graphs from the PDF, that's fine. If not, you are going to include your own graphs, which could be a picture or an Excel file again, or the same Excel file, and you open a new worksheet in it, or a new basically plot in it, and use that. As long as you include it, that's also in here. It's worth 6 points too. Okay. So everything else is typical except these two things that are a little bit different. So you really need to be mindful of those. So that is in terms of the grading and how this lab works. So let me open this file and I will see you when that opens, okay? So let me stop sharing that screen. And let's go to it. Okay, the first thing first is your name and anybody who worked with you on this lab. That is typical stuff. This is the discussion that we have had today, okay? We have a switch. This is just the charging in typical RC circuit. We have an EMF, we have a battery that pushes the current this way from the cathode toward the anode, basically. If you look at it in terms of electrons, the charges are actually moving in the opposite direction. The negative charges are being drained from the anode. They come to this side of the capacitor and they start to pile up in there. And on the other side, negative charges are being drained at the same rate and being basically piled up in here, but they can't pile up on a battery because the battery's role has an EMF, so it's going to push them in here, and the whole circuit continues as long as the EMF or the voltage in the capacitor is below epsilon. There will be a current. Okay. Once the voltage across the capacitor is exactly the epsilon in here, then you cannot put any more charges on the capacitor and the current stops in the whole circuit. So this is basically the process in a nutshell. We have seen this expression today, except Q max in here, we have written it C epsilon. That's exactly what it was. And the tau, which is really R times C. Okay, that's the time characteristic for this, or the times constant for this circuit. Okay. So in the charging stage, the voltage across the capacitor is given by this expression, because all you have to do is divide this expression by C. Remember, Q max is C epsilon. So if you divide it by C, you'll be left with an epsilon in here. So the voltage again across the capacitor is this much. When you are discharging it though, it's going to start with a certain voltage and start to lose. So in this case, when you're discharging it, and I wouldn't do this in lecture yet, but you don't have a battery in here. There's no battery, that's all. So you have an RNC, but it has a voltage. So if the positive charge in here and negative charge in here is going to push the positive charges this way, in practice, what's going on again is the electrons are moving actually from this side and coming to here. Now, this is not a battery. They will actually sit and stay there, and they will neutralize the positive charges in there. And they will continue to do so until we run out of charges. That's it. That's the end of it. This is not a battery. This is just a capacitor. So when you discharge it, the positive and negative charge, an electron, one measly electron by itself, it moves around the circuit. There is no battery now. We're discharging. We're in the second part that we're going to do on Wednesday. Goes through the resistor and then comes to the other side, find an ion and cancels it, and we're done. That electron cannot be pushed in here. That's it. Unlike the battery, which has energy and other processes, it will push them. But in this case, that's the end of it. So at some point, we're going to run out of charges. and that's it. And the whole circuit ends. So it's going to decay also exponentially with the same time characteristic. So it's going to come down, and then it's gone. That's it. If you don't reverse the voltage, or if you don't have a battery, or if you don't add something else, you're done. This will decay exponentially with the same time characteristic, meaning if I wait 1 tau, I would lose 63% of my charge. That means I'm left with 73% of it. If I wait 4 taus, I'm going to lose 98%, and I will be left with a little over 1.8%. 98, I would lose actually 98.17% to be more specific. Okay, that's the also. As a matter of fact, here are the numbers. Okay, 98.17 will be gained after 4 taus. This is actually a picture from the same GeoGebra that I showed you earlier in the day in the lecture. After 1 tau, this is typical. This is not typical. This is true all the time. The tau happened to be 2 seconds in this example. Tau usually of the order of a millisecond. Okay. The reason why I did it, like I mentioned in the lecture, choosing this high values for C, I mean, resistance 10 ohms is fine. I mean, 50 ohms is typical. Okay. You can't play much with the resistance. Sometimes you have even higher resistance than this. But the capacitance usually of the order of a microfarad. If you have a charger, for example, for your phone or for your, usually it's much smaller than that too. Okay, so this time characteristic could be very, very, very short. Okay, so that means you will wait a fraction of a second before you even blink. This whole thing is charged. It has reached 99.999999999%. Okay, that's a blink of an eye. So infinite in here is relative. Okay, relative in the process. So it's 2 seconds in this example. So if I wait 8 seconds, which is 4 times as much, is 98.17%. In other words, I have to tell myself, when can I say that I am happy with it being charged? 97%, 98%, 99%, 99.9%, 99.999%. So at some point, I have to call it a day and say, okay, it's charged. I cannot wait an infinite amount of time because no matter how long I wait, it's never going to be 100% really. But practically, if you use a device to measure voltage, for example, across it, you're gonna be within the margin of error. So you're gonna say, okay, it's charged. Okay. The math a little bit doesn't follow the logic in here with the physics. The physics will give you a number that is within 1/10 of a second. For example, this has a long time ago charged. So the math that we did earlier would work perfectly. I mean, the energy is balanced, everything is fine. The same thing is happening when it comes time to discharge. Now, this is a square wave power source. The EMF in this case is it has this meaning. Every 24 seconds in this example, the signal changes, meaning that it's for half a cycle, it's on. For the other half, it's off. Okay? It's on and off. Then after that, it's going to be on for about 12 seconds and then off for 12 seconds. So it's periodic, and the period in this case is equal to 24 seconds. The frequency is 41.67 hertz. That means it's 1/24. Okay? That's what this whole thing means. The signal is maxed at 10 volt, okay? Between 10 volt and 0 volt in this example. The 0 volt is allowing it to discharge. That means as if I don't have a battery in there, okay? We'll see how to work this one out in our case, in our lab. We will be actually doing it manually. We're going to actually flip the sign of the battery. So we're not gonna do this exact one. It's gonna go from, let's say, for example, positive 10 volt to a negative 10 volt. So we're gonna actually help it discharge more. Okay, we're going to help this battery to push the chargers more. So it's not only the capacitor, not only the capacitor put in charge to help it discharge, but I'm actually going to help it do that, to discharge it even further. Okay, so that's in a nutshell what the lab is. So that's basically what we're doing. Again, this is the so-called signal generator, and the signal generator is square wave. Okay. So we're going to simulate that in the lab. So at some point it's on, some point it's off. But as a matter of fact, in this case, it's sometimes it's positive epsilon, building charges in the capacitor, and the other times it's draining charges. And if we keep the signal going for a long time, it's going to actually build it in the opposite direction. So this is actually not a true DC current, because at some point, I mean, if you look at it only in one portion, half a cycle, it's really DC there. But it changes, okay? So this is kind of a tricky way of doing DC current, using an AC source. Although the alternating source in this case is not a sine wave, it's square, okay? So that's basically how this is. If we do the math, basically, it's going to give us this curve in here. So there is a discharge at some point, and there is a charge, okay? Now, actually, what I'm looking at, I'm sorry here, this is wrong, what I said in here. I'm looking at the voltage across the resistor. This curve in here is representing V sub R, V for the resistor as a function of time. Remember, the drop in voltage across the resistor is R times the current, I. So it doesn't matter what we're doing with a capacitor. We're looking at the current, because when we're scaling it by the resistance. So if the resistance happened to be 10 ohms, we're multiplying 10 by the actual current. That is what Ohm's law says. This is Ri. So this curve in here is telling me that the current is maxed, the voltage across the resistor is maxed, and starts to come down, okay? When I reverse the polarity, the current is going to be opposite now, maxed, and it's going to start to come down, okay? That's basically in a nutshell how this is working, okay? That is how this changes with it. So that's basically what we'll be doing in this lab. But of course, we're going to do it a little bit manually, because we don't really have actual stuff, okay? We are doing it in simulation. Again, you're going to state your objectives in here. This is part of the lab, okay? There is another part actually where we'll be checking this relationship. Let me find it. This one. Tau is a function of R. Typically in a lab environment, usually you have a capacitor. You change R, you change the resistance, okay? You take, okay, this, let's take the 50 ohms, place the 10 ohms, let's take the 10 ohms, place the 5 ohms, let's take the 5 ohms, place the 20 ohms, and basically you play with them, or for example, a 1,000 ohms. So you change R, and you see how you measure what tau is, and you see how that goes. So you plot now tau as a function of R, and it should be a line. The slope of that line should be the capacitance. So you compare the two, the actual capacitance that you have worked with all the way throughout versus the slope. If there is a match, that means this relationship works fine. If there is no match, that means there is an error somewhere, which could be explained, okay? So that's basically what we'll be doing the second part of this lab. So we're gonna be charging and discharging a capacitor. That's the first stage. And the second one, we're checking this relationship between the time constant and the resistor, the resistance, okay? That there is a relationship, a linear relationship, okay? And of course, the capacitance too, in a sense, because the slope is that of C. Albeit we're just varying the R in this case, like what we do in the lab. Like what we, if we meet tomorrow and they tell us, okay, COVID, there is no more, so you can come tomorrow and do this lab. This is what we'll be doing in the lab. You change R, and you're gonna plot actually tau as a function of R. Okay, so that's basically in a nutshell what we'll be doing. So let's go into, again, this one, I already provided that for you. If, on the other hand, you can go online and get it from there too. So if I click on this link, okay, let me stop sharing that and show you how this looks like. Where is it? Stop sharing. Let's go to the window that opened. All you have to do is download it now, okay? And it's going to look like what this picture is, okay? So instead of doing that, since I already downloaded and I included it as part of the Canvas download, you can download it from there, or you can use this link, okay? Now, let me stop sharing the screen because there is another interesting link that I want you guys to do too. And that is if you really did not have already a JRE installed on your computer, and that is this link, okay? So you need this one. That is also going to be sensitive to your computer. If you're using a Windows, depending if you're using a 32-bit or 64-bit, basically, depending on operating system. Same thing with what is it, Mac, same thing with Linux, whatever machine you have, it should be sensitive enough to it to download the right stuff for you so that you run it. Again, without this one, you're not going to be able to do the lab. So this is a necessary step you have to do, okay? You have to do that. Once you do that, then you can open the file, okay? So I'm going to open the file just as if you just did open it yourselves, okay? And then I will take you there to it. So let me find where it is. And here it is. So let me open it and make it bigger. And stop sharing that screen and share with you this screen. So this is how it looks like when you open it, okay? It says to grab a wire. That's fine. You don't need to grab. So the first thing I would do is stop the animation from this play button. It's the two basically lines. So now it's stopped. Now I can do things, okay? Now I can come and do stuff. Okay, the first thing I'm going to do is trying to make it look like as if this is what it looks like. I really don't like that. I think it's too phony. So I'm going to go to the schematic. Okay, number one. I like to show values, and you will notice that when you do show values, sometimes they don't really show, they go away. So you really need to do them. Leave the voltmeter later. Okay, you can do it now, but leave the voltmeter for right now later. But once you have everything lined up, okay. Depending on how you like your screen, you may choose a larger size, small size. That's really irrelevant as far as that. The thing that I need to do now is show advanced. Okay. Once I do that, flashes a couple of times, I need to take the wire resistivity to something a little bit more interesting. And then I say hide electrons. If I don't do that, look at this wire, for example. I'm going to grab a wire. It's showing me electrons in it. That is, actually too artificial. Okay, so I'm going to hide the electrons. It looks like it's a normal wire now. So I drag the wire. I'm going to put it in here. Oh, I'm sorry. There is another thing that I need. There's the stopwatch. Once I bring the stopwatch, I need to start it right away. Although it's not running in here, that is because the animation is not running, okay? So when I say play, it's going to play. And that is the advantage of doing it actually on here. That is the only advantage of doing it online. Otherwise, if we're doing it in practice, this is not going to work that way, okay? There are a couple of things that probably you can play with later on, but I found them very useless because they don't really give me the numbers. They just basically display how the signal look like, as if you have an oscilloscope basically and looking at it. So ignore those two for right now. So I grabbed a wire. Now I need a battery. No, I'm sorry. I need the resistor. So I'm going to drag a resistor to the circuit. And the resistor, as you can see, because I'm showing values, is 10 ohms. That's not what I want. The lab instruction says to right-click on it. I right-clicked on it, change resistance. I change resistance. And I drag the slider to about 50 ohms. Actually, it has to be 50 ohms. Exactly. You can enter it manually too, which is a lot easier than having to drag that thing there. So now I have 50 ohms. You see what I told you now? Once you enter something, this show goes away. So don't forget to do that at the end to make sure that all of your values are there. I'm going to drag another wire in here. Okay. Make it short a little bit. And then I'm going to drag my capacitor. So here is my capacitor. Again, it's 0.1 microfarad. I'm going to right-click on it, and I'm going to change the capacitance to the max. You cannot do anything about that. So it's 0.2. Again, to give me time, I know it's the time characteristic in here is going to be 50 times 0.2, which is going to be 10 seconds. So that gives me time to control this whole experiment basically and play with it. Okay, again, this is because we are online. This whole simulation, I should say. Okay, I'm gonna connect a wire now. Make sure when you bring it, it snaps to the position in there. I'm gonna take another wire just to make it look like it's make it a little bit shorter. And now I'm gonna drag my my battery. The battery right now, the anode is on this side, the cathode is on that side. That's fine. That means I'm going to pile up positive charges on this side and negative charges on the other side of the capacitor. But I have to right click on it and change voltage. When I do change voltage, I notice that the maximum is 100 volts in here. So I'm going to check for more volts, and I need to make it 120 volts. The reason why I'm doing that is because I want to have as much precision as possible, okay? I'm going to put 120 volts to give me room basically for my voltmeter to have as many decimal points as I can. Again, this is probably too much of a battery in here. So right now it's 120 volts. I'm going to bring another wire in here just to complete the whole thing. And more or less in there. And finally, I need to place a switch in here. Oops, Control Z. Place it on the wrong way. Oh, I can't do that. I have to click on it. Man, split junction. Bring my wire out and spin this one a little. And man, this is something that could happen to you. Now it's connected, that's fine. And except that it's, now I closed this. I'm sorry, should not have done that. It's fine. Practically, you don't even need it for this lab because of this time stoppage that you can control from here. But in a real lab, you would need that, okay? It's not good to have things running out of control, okay? So now, actually, it's reading 0 ohms. Right now, it's reading infinite amount of ohms. Right now, it's 0 ohms. So basically, right now, it's open. Now it's closed, okay? So close it. So at this point, we're ready for the animation. If the numbers do not show, please check and then check it and check it and check it again to make sure that the numbers are as is. You have 120 ohms. I'm sorry, 120 volts. This is an ideal battery. That means it has 0 ohms. The capacitor is sitting at 0.2 farads, and the resistance is at 50 ohms. At this point, I'm going to bring the voltmeter into the equation here. So when you click on it, it's going to come back by itself. It is very important that this side, the black side, if you wish, where the COM port is, connected to the negative side where the battery is, okay, on the resistor, okay? And you bring the positive side in here where the volt is supposed to be coming and reading, and you connect it to the other side, okay? And why it's not connecting? Sometimes you may run to this situation because it's supposed to snap, and it's not snapping to the correct place in here. Unless you are reading a 0 volt in here, this is useless. So right now I'm not getting a 0 volt. I'm going to try to put it in here. This is the problem with this animation. Okay. I'm going to close this one, I'm sorry, because this is typical what happened to it. And I'm going to reopen it and do it quickly, okay? Okay, so let me go back again. Unless we do that, unless we get a 0, actually, where is it? Okay, here it is. It was not showing as an option. Okay, so again, schematic. Let's pause this thing in here first. Schematic, show put this one a slightly, then let's put the resistance, the wire, capacitor, the wire, another wire in here. So it's supposed to snap in place, and sometimes it doesn't. That's one of the things I hate about this animation, is because it doesn't give you full control over things sometimes. Okay, make it as big as you need. Bring this one into this side. Bring the switch in. Rotate it first. Let's rotate it this way so that I can close it from the other end. That's fine. And let's bring another wire now. Okay. Let's add the stopwatch. Change the values. So this is 50. Okay, what is show values? Yeah, it's 50. Let's change this one, make this match as possible. You have to click on the object first, okay? Click on it and then right click and change. Oh, I'm sorry. Nobody may said anything about this. Remove. We don't need we need the actually battery in there. Okay. So change 120. Okay. So we have 120, 50. So let's bring now this guy. Oh, wow. I don't know what's going on with this animation. Sorry, guys. Okay, I'm gonna do the following for you guys. Okay, you have to have a voltmeter in there. Let me see if I can. Load. The only explanation I have right now is, okay. Let me see if this would help. The only explanation that I might have right now for it is that probably it's not. It's in full view, so it's in full mode. So maybe that's why. Okay. So let me stop sharing. Start sharing the screen. Or did I? I think the problem now, because now it's working. Okay. It's giving me a reading. This is what I want to see, a reading in the voltmeter. Okay. So let me. I think the problem was, and I'm not 100% sure, honestly, is the fact that we remove this one voltmeter because we don't care. Okay, so because I think the when you are in full mode, this thing was not snapping in right place. Okay, these two were not snapping in right place. So again, try it. Try to do with this one as much as you can. Let me remove this electrons. Okay, give it some resistivity. So the way it's supposed to be anyway. And there's just an ammeter, which we can remove. Actually, we don't need. Okay, and probably the switch also. So let's remove that and bring a switch in the expression here, just to make it look like. Okay, we're gonna close it anyway. So, okay, now we lost this thing in here, did we? Okay, good. Okay, the point being in here is you're supposed to have a reading in here, so probably I should let this one go all the way to 0. Till there is no current in the circuit. I could have done a little faster by either decreasing the value of R or changing the value of C. So the voltage right now is 4 volts. I'm supposed to have 0 volts in there. At some point, there will be too much things, so I really have to. And there is something in here. I'm not sure if it works or not. Where is reset all? I didn't mean that for it to happen. What is this? Anyway, you're supposed to follow the instructions, get that resistor working, and try to do it in the minimized mode, okay? Try to do it in the minimized mode. And because right now I'm getting a voltage, although there is nothing in here. So let's reset dynamic. I don't know what that is. So, and even if I reload this one in here, it's going to get me the same thing in here. It's get me the same voltmeter. So the voltmeter is continue going to read this number in there, okay? It remembers the last value, although probably you should have 0 in the whole thing in there. So I'm gonna continue with this one. Oops, why is it 112 now? Some of you enjoy when things don't work well, okay? Actually, it's usually they're a good learning thing. But this simulation, honestly, I don't think that there is physics or math to learn from, unfortunately. It's just a simulation because it's the person who set it up did not set it up correctly. Fortunately, this is from the University of Colorado, so I really don't have any access to source code or anything like that. And honestly, I don't even know what code. I think it used Java. Yeah, it used Java. So it's precompiled somewhere in there. Somebody has the source code. Okay, so we'll wait for the current to be to 0. Right now, 0.02. It's going to slow down drastically because this is an exponential decay. 0.01 now. So it's going to be very, very slow, reaching 0. I'm going to stop it in there because right now I have 0 current. Okay. So if you want to have as small as possible value, we're gonna wait for it. Okay, so it's gonna take forever now to come to 0. That's good enough. But what I'm going to show you guys is I'm going to reverse the polarity of the battery so that we have data for our case in here. Albeit this data is going to be negative first, so we're going to record it as positive, at least for my case. For your case, you're going to have it positive the way it's supposed to be, okay? Okay, 0.01 volts, so it's practically no current whatsoever in the circuit right now. I stopped the animation. So what I'm going to do in here, I'm going to right click. Let me make sure the values are the ones for the experiment. Everything is according to the experiment. So I'm going to reverse the polarity, okay? So now I have 0 current. So that means this whole thing is probably fully charged. Let me see in here. This has 120 volts right now. So we're starting with the second part right now. So let's bring it back. So I have 120 and 120. I should be pushing 240 volts. So the voltage now should start with a high current, extremely high current, and then starts to come down. Okay, but it's going to be negative. It's going to be in the opposite direction because both of them are pushing in this direction now, not the initial direction. So in other words, a positive in the wrong direction. But I'm going to keep it the way it is. I'm going to keep the COM terminal to be connected to the cathode now. So the numbers are going to be negative right away, and it's going to be a huge number. So again, I'm going to start this one in here. And I'm going to, for this case, okay, start the animation, immediately stop it. So start it and stop it. As I said before, it's a negative 200 and something. Because remember, I have the battery, which is 120. I have the EMF across the capacitor, which I fully charged initially, okay, in that process, to about 120 volts. Then both of them are pushing current in this direction. The current actually is coming this way. So this thing in here is reading it backward. That's why I have a negative number in here. So this is the second part of the lab after you fully charge. So we're actually starting with the second part in this particular classroom, the way that I'm doing it right now. Because initially I was building charge in it when the current drops to 0. Then now I'm building charge. So what I need to do now is record to time. In your case, it's going to be 50 seconds, 50 minutes plus. 50 seconds plus this much. So it's going to be 50.63. So for me, it's 0.63, but I have to add to it 50 if I did it correctly, okay? And then I have to wait for any time. So I'm going to record the value of the voltage, which is negative 200, and you have to keep the sign. So it's going to go. Let me stop the share. Let me show you what I'm talking about in terms of the table. Let me go back into the PDF file and show you where that data need to go. If I followed the correct reading and I have 0 volts in here, which for some reason it did not snap in place for me, okay? And I followed the steps in the table, I needed from 0 seconds to about 50 seconds, I need to be filling this side. So this is going to be, let's say, for example, 1 second or 1.2 seconds or 0.7 seconds or something. I'm going to put the time in here, and I'm going to put the voltage in there, okay? So the voltage initially will be very high because when I'm charging, I start with only 120 volts and there is no voltage whatsoever in the capacitor. So the only thing I will have is about 100 volts in there, okay? And so most of the voltage will be in the resistance to begin with. So at t equal to 0, exactly it's going to be 120. But I didn't catch it at t equal to 0, I caught it immediately after. So it's going to be roughly about 120, slightly less than 120. And then I wait for about anywhere between 10 and 20 seconds. 15 seconds, 14 seconds, 12.7 seconds, 16.3 seconds. It doesn't matter when I stop it, okay? I'm going to read the voltage in here. So it's going to drop from 100 and something down to probably about 80 volts or something. So I'm going to record the value in there. Wait anywhere between 20 and 30 seconds and stop it. So once I stop it, the reading now should drop about 40 volts or something in here, okay? No, actually probably the first one maybe 100 and something. The second one I probably would have about 60 volts or something. The third one will be about 20, okay? The fourth one, I will wait anywhere between 30 and 40 seconds, okay? And the reading probably will be 7 volts or 6 volts or something like that. Remember, this is an exponential decay. The last one is between 40 and 50. Not 50, slightly less than 50 if you like, 46 or 47 or something like that. Seconds. Then I do the reading. It should drop now to about 4 volts or 2 volts or something like that in the voltage across the resistor. Now, if I divide that by 50, I'll find the current to be a very small number, okay? But I don't care for the current. I'm looking just for the voltage across the resistor. Now, what I do there is exactly what I did when I did reverse the battery. I wait for it around 50 seconds. I hopefully catch it around 50 seconds. So in other words, I play the animation until it reaches 50 seconds or immediately before or after it, okay? That's why I did try to do this time as big as possible to catch it and do the signal ourselves, to control it ourselves. Right click on the battery and reverse its polarity. Now, that's exactly where we are right now in the process. We are supposed to be anywhere after 50 seconds. I know I did not start the time, I just started it. So it's giving me 0.63. So let's say, for example, I was successful and I did it exactly at 50 seconds. So this time should be 50.63. Again, I don't mess around with the clock watch. Once I start it to begin with, I should not touch it anymore. The only thing I need from it is the reading. So if I did it exactly at 50 seconds, this is how much it would read on the stopwatch. It would tell me 50.63. The voltage right now, I think it was what, negative 225.346. Negative, and again, you need to keep the negative, 225.346, okay? That's why I needed this high voltage also to get as much precision as possible, okay? By the way, this R is 50, and this, in microfarads, remember 0.2 is about 200,000, okay? I need to enter it twice. This was part of a lab where I actually do measure the capacitance twice, and I will have two values. So technically, I should find the average value. So I just took it from that lab and left the numbers there because I'm fixing it manually. So please enter the number twice. Otherwise, you will get a huge error in here, okay? So 200 and 200, both of them, 200,000, 200,000. And it's supposed to be in microfarads. If we're doing this in lab, it's probably 100 microfarads or something that we will be operating with. So I will put 100 in there, but this is 0.2 farads, which is 200,000 farads, okay? This is 120 volts. That's basically what we have to fix. This is the time we flip it in. It changes every 100 seconds. So every 50 seconds, we have to change the polarity manually. So this is what this is saying. The time, this is 100, the frequency is 0.01. That means the period T is 100 seconds. That means every 100 seconds, the whole process is supposed to reverse again. If we actually are in the lab, okay? This is what happens. We're going to do it by itself. Albeit in the lab, we'll be probably using a much, much higher frequency, meaning a much, much shorter period, because this tau is so small. So we need to catch it in between, okay? So in the lab, this whole experiment is done differently, but the simulation is trying to catch it manually so that we do the flipping ourselves. We change the signal ourselves. So at 50 seconds, half this time, half the period, we should change the signal back to the polarity from a positive 120 volts to a negative 120 volts by reversing the polarity of the battery, okay? So we are in that stage right now. So let me just get another reading in here to show you how this will go. So I'm going to wait now. Remember, we are at 50.63. So now I'm going to wait between 60 and 70 seconds. So I'm going to give it time. Right now it's at 53, 54 seconds, 57 seconds, 59 seconds, 60 seconds. Any time after that is good enough, okay? So right now is good probably. I think I waited too long, but it's fine. 67.25. I have a negative 42.761. So I go back into my data in here and put 67. The time is 67 point. Let me look at it again. 0.25. 0.25. And the volts as negative 42. Negative 42.761. Okay. And you continue until you have 5 readings. The last one, you should not exceed 100 seconds, okay? So the second one is going to be between 70 and 80. The third one between 80 and 90. And the last one, you should do it immediately before 100, okay? Do not wait past 100 seconds, okay? Because then you will have a, you technically there when you're supposed to flip the signal back again, okay? So technically that's when the signal should flip back again to the other side. So that's basically how this whole lab works. Again, we missed this one. Actually, we can let it run until we are in that stage. We go back in here so that we can get data in that side. What is the animation here? No. Here. So I'm going to let it around 50 seconds, namely when this current goes back to 0 again. Okay. Namely where this voltage drops back to 0 again, because the current is dropping back to 0. The voltage across this capacitor now should be going down now. I'm sorry. Are we building it now in the opposite direction? Yeah, we're building it in the opposite direction. So we're always going to be building charges. Okay. Ideally, this lab should have been started. Let me stop this thing in here. Okay. Ideally, this lab should have been started backward. Okay. Again, if you guys have difficulty with it, please let me know. And I will probably try to build the simulation and share it with you guys, okay, on Canvas. So rebuild it from scratch and make sure that the voltage is reading 0, the whole thing is 0. Actually, if you follow the instructions, you can do it on yourself, okay? And this is actually part of the lab anyway, so that's what you're supposed to be doing. If you follow these steps, you should be able to get all of these things working. The only difficulty with it is sometimes that thing with the voltmeter doesn't give you a reading. It should read 0 because it's snapping. It's not snapping properly. Okay, try it please once, 2, 3 times. Usually it works like right now. Okay. Once you have that, you have the voltage. You reverse it, and you're done with this part. You're home free. Now you take this data and you run it on Excel file, okay? So let me show you how the Excel file would look like. Okay, so let me stop sharing that screen and bring you to this Excel file now. It's the same things. I think here was 50. This is 200,000, 200,000, 200. It gives you already the theoretical value, which is actually a question that you're supposed to answer anyway. Okay, it gives you the EMF. And these are the times from 0 to almost 50 seconds. The voltages are going to be from almost 120 volts down to 0. And these are the times from 50 to 100 seconds, the voltages are going to go from negative 200 and something down to about 0. Okay, and that's basically the entire process in here for how do you charge and discharge basically this lab. The Excel file will give you the charts. Okay, if you did everything. This is just for the calculations and how things are going, okay? The Excel file will give you the theoretical and the experimental for tau, and will give you the error in here. It's also going to tell you how much effectively the voltage of your battery was. And it's going to compare it to the 120 that you manually inputted in there. And then it's going to give you the percentage error with this. Take these numbers that the Excel file gives you and transcribe them back into your lab. So you take what this value is, it's already 1.00 times 10 to the power 1 seconds, and the experimental value will come from your data. This one is 120 volts. It comes from this one. This one again is going to come from your data. It's going to report the error value in here for between the tau theoretical and the tau, which you can calculate by yourself, by the way, if you refuse to do the Excel file, which is fine. I mean, you're going to lose 6 points, but this calculation is easy to do. The difference between the two divided by this theoretical value and times 100. That's going to be the percentage error. Same thing in here for the percentage error for the EMF. So now you have all of that. You're going to answer this question based on your measurement. Compare the time constant you calculated in question 1, because question 1 was supposed to calculate this time constant. Okay, tau naught. Tau naught, since you know now the values of R, which is 50 ohms, and the capacitance 0.2, you multiply the two and you should find the time constant, okay? Don't forget the units. Now you're supposed to compare the two. Here is the theoretical. You're going to state basically the theoretical value was this, the experimental value was this, and the percentage error is this much, okay? I'm warning you, if the error is above 5%, you really need to do this lab again, because I know, I mean, redo the, some of these data probably was not reported correctly, because I know that this error is less than 5% for this one, okay, for tau, because that's all we care for. If the other one is more than 5%, it's not important, okay? What is important is in here. Then once you have that answered, you're going to come to this expression here. This is just to calculate. This is exactly what we did in lecture, okay? Because now you know the expression for the current, which is given by this equation from lecture. And actually it's in here in the notes too for the lab instructions. Let me go back into this view here. So, since you know what Q is during the charging cycle, or even the discharging cycle, you can take its derivative, and now you have the current. You multiply the current by R, and you have now the voltage across it. So it's going to be a constant number, whatever that constant number is. It's relevant for the next part, for the next portion of the lab. Because in this portion of the lab, now you're trying to effect of resistors on time constant for RC. So that constant actually is not going to matter, which is just the voltage divided by time divided by RC times times R. Again, it's not going to matter really, honestly. So that's why all you need is just a constant, whatever that constant is, times the exponential. Okay. Okay. Now, this is important. So you have V1 or VR at T1 for the time T1, and you have VR at time T2. So you're going to make two equations and solve for tau. Okay. And this is actually what the solution is. So you need to show that this is true. That tau is actually the time difference between a later time and a prior time divided by the ratio of the log of the earlier voltage over the later voltage. Because the earlier voltage is higher than the later voltage, this log is positive, and this is later time is past the first time, so this difference is positive. The ratio of positive over positive is going to be a positive number. So that is what the time constant is. You will need this expression, even if you don't answer question 4, for this part. Because what you're going to do in this lab, portion of the lab, you're going to take 3 readings per ohm meter. So you're going to change the ohms from 50, 20, 10, and 5, okay? While doing, when you do that, for 50, for example, you take 2 readings. Time, 3 readings, I'm sorry. Time, for each reading, you are going to take 2 pieces of data. You're going to take time and the voltage across the resistor. So don't change anything with the lab. Keep everything the way it is. So you don't have to change. The only thing you change is the resistance. As a matter of fact, the first part, you don't even change the resistance. It's the same resistor that you have been working all along. So you're going to take a time, the voltage, time, voltage, time, and voltage. Use this expression to find tau. So the first tau is this time minus this time divided by the log of this time, this voltage over this voltage. Using this expression, now you have found tau 1. Okay? Use the same thing, this expression, this time minus this time divided by the log of this term over this term. Now you have found the second one. Find their average. Change the ohms to 20 and redo this calculation. 10 and redo this calculation. 5 and redo this calculation. Now you have 4 taus for each one of these resistors. Tau for 50 ohms, tau for 20 ohms, tau for 10 ohms, and tau for 5 ohms. These are average values. Okay. Now you have the 4 values. You're going to plot tau as a function of R. So R now is 5, 10, 20, and 50. So you need to scale it correctly, okay? You can use Excel for that if you like. And then now you have the taus. It should be a line now, okay? Find the slope of that line, and that is actually the capacitance. As a matter of fact, that's the next question, okay? You're going to compare C. Remember, C is 0.2. It never changed. So now compare the slope to 0.2. Basically, they should be within the difference between them. That's the error, okay? So that's, again, the experimental value minus the theoretical value, which is 0.2, or the known value, which is 0.2, divided by 0.2 times 100. That's the error. Okay, the error is an absolute value, so there is no positive or negative. And that is the whole lab. After that is your conclusion. The biggest headache for this lab is getting your simulation working. Any questions? Okay, if you guys don't have any questions, I'm gonna see you guys, unless some of you want to do it now, because I know that you have exams and you have actually quizzes and other things to do for this class. So we're going to meet again on Wednesday, and hopefully some of you would have started on this lab, if not next week. Any questions for me before we end this session? Thank you, Sebastian. Yes, go ahead, Alex. What's the question?
Can you hear me?
Yes, I can.
It's for the homework, 26. Like, there aren't any assigned problems.
Oh, it's not assigned yet? I thought I had posted them, no?
It's just there, but there's no problems. Like,
okay,
assigned.
I'm gonna put them right now, okay?
Okay.
I'm gonna put them right now. I'm sorry, I thought I put them because they're already part of the assigned stuff. Okay, I'll work on it right now. Thank you.
Thank you.
Okay, bye. Okay, see you guys.